எதுனாலும் பரவாயில்ல, இங்கிலீஷ்னாலும் பரவாயில்ல, தமிழ்னாலும் பரவாயில்ல.
அது ஒன்றும் பிரச்சனை இல்லை ப்ரோ. நீங்கள் எதில் கம்ஃபர்டபுளாக இருக்கீங்களோ எடுங்க.
சரி, ஓகே. Just to set the context, actually, in this particular presentation, right, like we are going to see attacks only on predictive AI. So if you Google about adversarial attacks on machine learning systems, right, there will be like multiple attacks on like, say for example, generative AI, like LLMs, and there will be like, you will also get a SANS presentation on the common attacks affecting machine learning models. So they, and in that particular SANS presentation, there will be two category of attacks. Like they would have categorized the attacks based on two particular categories. Like one is predictive AI, attacks on predictive AI, and another one is attacks on generative AI like LLMs and other things related to LLMs, like for example MCP security. So attacks on LLMs and MCP security, already we would have seen multiple links, blogs, uh, all over the internet. Like we would have access to multiple free labs for specific attacks on these LLMs, specifically generative AI related attacks, and also we have top 10 for LLMs. So in this particular presentation, we are not going to see about generative AI related attacks like prompt injection, indirect prompt injection, excessive access, MCP security. Now we are not, like, I'm not going to cover those particular attacks related to generative AI or agentic AI security like MCP. This is specifically related to predictive AI, like attacks on machine learning models that are used for classification or making predictions on real world scenarios. Say, for example, for machine learning models being used for autonomous driving, or machine learning models used for image classifications. Okay, so we are going to see only two set of attacks. One is model evasion and another one is model poisoning. And these, like, just to set the context, this presentation is about only attacks on predictive AI, not on generative AI or other related things. And one more thing is, like, I'm not a machine learning expert. I'm not into machine learning and all. Uh, I recently started learning about machine learning and all these attacks like last month. Having said that, I can explain all the machine learning related topics in a way everyone could understand. I will give practical examples. I will explain with context, like with real life context, like like for example, I will give you example for each particular topic, but I don't have knowledge, or I cannot explain the intrinsics of each particular topic, like machine learning. Like for example, neural networks, for example, I know the very basic, like what is the application of deep neural networks or something like that, but I cannot explain how exactly deep neural networks work because I'm not into machine learning. Just to set the context, but I will explain in a manner everyone could understand in an easy way. Like I will set real time examples. Coming to the, yeah, feel free to like ask questions in between if you don't understand any particular explanation or any particular topic or something like that. For example, like machine learning models, like most of us would have a very basic idea about what exactly is a machine learning model. I will give a very basic example. Say for example, if you want to teach a child on recognizing fruits, like different fruits like oranges or apples, right? You show the child different images of like oranges or apple, or different fruits, right? So over a period of time, the child will be able to say you show YouTube videos or you show the images of different fruits to the child. So over a period of time, the child will be able to understand and differentiate between different fruits, and child will be able to recognize fruits like apple, oranges, like that, based on the shape and color of those fruits. So similarly, like in very similar terms, say for example, I'm training a machine learning model to identify spam emails. So like the context is, I'm training a machine learning, I am training a machine learning model to identify spams. Okay, so what I will do, right? So I will give this machine learning model vast amount of spam mails. Like I will give like a number of like say for example, first of all, we have to create a data set of like different spam emails, like used by different threat actors or APTs, like that. So we have to create a data set of different spam emails, and then we feed these different spam emails to the machine learning model. This machine learning model identifies patterns within the spam emails. Say, for example, what is the pretext that is being used in these spam emails? The URLs mentioned in these spam emails. What is the reputation of the domains associated with those URLs? Or say, for example, what is the attachment? Like in case of spam emails, what is the most common extension type or attachments that comes with spam emails? So it identifies patterns within these like a vast set of like massive data sets of spam emails that we are feeding into the machine learning model, right? So it identify patterns like these all these scenarios, and based on that learning it will be able to take decisions. Say for example, based on the learning it has received, right? Well, we can give it a mail and ask it whether we and ask it to classify whether it's a spam email or not a spam email. So there is only two sets, like whether it's a spam or not a spam. So based on the training it has undergone, it will be able to make predictions or decisions. So long story short, like in very simple terms, right? Machine learning models is something like we train it on massive amount of data set, and based on the learning, the machine learning model will be able to make decisions or make predictions in real world unforeseen scenarios. That is the idea behind machine learning model. So I mentioned that training right in the machine, like in order for the machine learning model to make predictions, right? We give it training actually. So these are the major classifications. This is not like a I would say comprehensive list of training types, but these are the major classification. Like in supervised learning, right? I mentioned. Say, for example, here we can take an example of image classification machine learning model. Okay, so in that scenario, we give it different images of, say, for example, dog or cat, and we explicitly say, for example, if we are giving an image of a dog, we explicitly label it as a dog. If we are giving the image of a cat, we explicitly label that image as a cat. So the machine learning model will be able to understand the patterns within the image, the pixel values. Like one more thing, we have to set the context, right? So like how humans perceive images or objects is different from how computers or machine learning models perceive images. So we can recognize objects, but the machine learning models or computers, they will be able to, they cannot, they don't perceive images in the same way as we do. So in that scenario, these machine learning models identify patterns in the images or the training data sets that we feed to it. Okay, so in case of the image of a dog, it will identify pixel values or patterns within the image, and it will match it with the dog. In terms of a image of a cat, it again identifies the pixel values and different shapes, different patterns within that image, and it will match it with the cat. It doesn't know what is an dog or what is a cat. If we explicitly say, if we flip the label or if we change the label, we give it an image of a dog, but we change the label to cat, it will start interpreting that dog as a cat only, because it doesn't know the context. We have, based on what it has learned, it will be able to make predictions. So if we explicitly change the category from that of a dog to a cat, it is going to recognize the image of a dog as a cat always, once the machine learning model is into production, or like you can say like during inference, right? It will always classify it as a cat. Supervised learning, that we are going to feed it massive amount of data sets with explicit labels. Say if you are giving an image of a dog, we explicitly label it as a dog. If we are giving an image of a cat, we explicitly label it as a cat. So it will in that scenario, it will be able to identify patterns within it, and it will be able to match it with the label. It will match the patterns it has identified within the images with that of a label. So this is an example of supervised learning. In under that, when or what particular which particular day or what period of time, like whether in daytime or night time, when is the transaction being made, from which location is the transaction being made, um, what is the usual amount that is getting transferred. Okay, but say for example, if a malicious if the user gets hacked, or some amount of money gets transferred to a foreign country, right? That is a pattern that differs from the normal pattern. So this particular machine learning model has already identified patterns, like what this particular user used to do transaction only during this particular time period, and you're usually used to transfer only, like say for example, you transfer one something like 50,000 or the 1 lakh to 1 lakh. Suddenly if a transfer something like, if he transfers something like 5 lakh or 1 crore or something, that is something malicious. So it will this particular machine learning model will be able to identify patterns and deviate the like identify deviations from the normal pattern. So based on the time and as well as the amount that gets transferred, or say for example in this scenario, if the amount is being transferred out of India, so that is a different transaction that deviates from the normal pattern. So it can identify these kind of this particular machine learning model can identify these kind of fraudulent transactions. So that is an example of unsupervised learning. Reinforcement learning, an example would be autonomous driving, like autonomous cars, these machine learning models used in autonomous driving, right? So within an environment, these models learn how to do like acceleration, braking, steering and all, right? And real-time feedback would be given to these machine learning models. Say for example, if the model is doing good driving, right, like without hitting any obstacles or objects, it is obeying the traffic signs, then rewards will be given to the machine learning model, like some kind of points, right? Like environmental feedback would be given to the machine learning model in real time. Or if the machine learning model fails to interpret traffic signs, or it causes a collision, during the test simulation, right? Then penalties will be awarded to this machine learning model. So based on the real time feedback that is given to the machine learning model, it will be able to learn on its own and apply that learning to the actual on road scenario. So this is an example of reinforced learning. Another example would be like some AI tools that can play chess or any other games, right? Any AI tool that can play human games, right? So again, feedback will be given to the model on how to crack that particular game, and based on the learning, it will be able to match the game skill set of a particular user. This is an example of a reinforcement learning. Any questions here?
சோஃபார் நன். இல்ல ஏதோ கொஸ்டின்ஸ் இருந்ததுன்னா சாட்ல போடுங்க, நான் வந்து ரிலே பண்ணிடுறேன்.
Okay. Okay. Now, like before we move on to the attacks, let us understand some concepts actually. So these are some concepts that we need to understand before we can move on to the actual attacks. So in order to execute that attack, right, we need to understand these basic terms. I will explain these like rather than explaining the textual description, right? I will explain each of this particular topic with an example. So let us take a machine learning model that can predict real estate prices actually. Okay, so in this particular, for this explanation of this concept, right, for the explanation of this concept, right, I will give an example. Machine learning model to predict real estate prices. Okay, so this will take input as this machine learning model will take multiple inputs like 2 BHK or 3 BHK. 3 BHK. Okay, proximity to the road or city. Another one will be plot area. Okay, so this machine learning model will take in these inputs and it will predict the price in a particular area, like whether it's 1 crore or 1.5 crore or 2 crore. It will predict this is the functionality of the machine learning model. So now, model parameters. So in neural networks, there are concepts like weights and biases. I'll explain what is a weight. Say for example, for this particular real estate machine learning model, right, to predict prices, we have to give importance to these particular terms. Say I want to give much importance to the size of the house, which is a 2 BHK or a 3 BHK, or if it is close to the city, the price of the house should increase, right? If it is close to the city or if it is close to the main road, right, the price of the house will increase. And then based on the plot area, like whether it's 1,000 square feet or 2,000 square feet, the price will increase. So if you want to give importance to these particular parameters, right, you want to instruct the machine learning model, give importance to these parameters in determining the final price. That can be done using concept called as weights. Sorry, concept called as weights. Oh, sorry. I'm explaining it theoretically, but in terms of neural network, weight means they will assign some numerical values to these particular parameters. They will assign some numerical values to these particular parameters to instruct the model to give importance to these parameters in determining the final price. Okay, that is the idea. I am just explaining here. I'm just giving a theoretical explanation, but in terms of machine learning model, this will be weights and biases, everything. Like I think weights and biases, loss function, gradients, everything will be numerical values in terms of actual machine when it comes to machine learning models.
Bro, I have a question.
Yes.
So by weights, they assign values like 1.0 for 2 BHK, 1.1 for 3 BHK, and so on, right?
Yes. Sorry.
Yeah. I asked the scheme will be like they would be assigning 0.9 for 2 BHK, 1.0 for 3 BHK.
Exactly. Yeah.
Okay. Okay.
Yeah, I said that exactly. That is the answer. Like it will be like they will be assigning some numerical values to instruct the model to give importance to these particular parameters. As Aravali mentioned, it will be like a kind of those numerical values. So now, like weights are, as I mentioned, weights are meant to give importance to these particular parameters in determining the final price. And offset. If you see, there are two things: weights and biases. Sorry. You are able to see the text file also, right?
Yes, bro. No
Uh,
issues. We are seeing the sublime text.
okay, okay. Offset. Say, for example, offset biases are meant to offset the final prediction of the model. Say, for you want to increase the final prediction of the model by a certain percentage, or decrease the final answer of the model by a certain percentage, plus or minus, I would say, plus or minus. So you want to increase the final percentage. Like, say, this particular machine learning model comes up with a price of like 1.5 crore. You want to increase the price by 10 percentage, or you want to decrease the price by 10%, 10 percentage. Then you will use a term called as biases. Again, this is a numerical value. As Aravali mentioned, you will give some values to it, and based on that, it will offset the final price of the house by either 10 percentage or 20 percentage. It will either increase the price or decrease the price. To give an accurate example, say for example that if this particular house, right, comes up within a gated community. So if it is within a gated community, it will come with multiple amenities, so called multiple amenities to fool the customer. Okay, basically to fool the customer. But if there are multiple amenities, increase the price of the house by 10 percentage, right? Or if there are no amenities, so this is not within a gated community, this is like an isolated 3 BHK villa or something like that, right? A completely isolated 3 BHK villa. Then decrease the final prediction, which is the price of the house, by 10 percentage. So based on with or without our amenities, we can increase the price or decrease the final prediction of the model. Okay, so that can be done using biases. So using biases, we can convince the model to give, like, do this or do that in the final prediction, kind of offsetting the final prediction of the model. This concept is clear, right? Weight and biases. Okay. So last function, like final prediction. Say for example, final prediction. The model predicts the price of the house is like 1.5 crore. Okay, but what if the actual cost of the house, actual cost uh, is 1.3 crore? Okay. The actual cost is 1.3 crore, but the model is predicting the price of the house as 1.5 crore. So there is a difference between the actual cost and the prediction, right? So we need that. This is an error from the machine learning model perspective. That model perspective. This is an error from the model perspective. So again, this last function, right? Last function, again, it is a numerical, I would say numerical value that is used to measure this error, like how the final prediction is deviating from the original value or the accurate decision, accurate prediction, right? Accurate value or the exact results. So how exactly or how much the model's prediction is changing from the actual value. So this last function is used to measure that particular deviation or error. Again, it's a numerical value, like it will be something like a 3 to 1 or like 100, something like that, or 1.1, something like that. Just for understanding purpose. Okay. Gradients. Gradients, like see, in case of machine learning model, we are going to give some inputs to it, and it will analyze the inputs and it will give a prediction. Okay. So here, from a developer perspective, while training, he will give multiple inputs to the machine learning model, and he will try to reduce the loss function. Okay. He will try to reduce the loss function because he wants the machine learning model that he created to give accurate results. He doesn't want the machine learning model that he created to give inaccurate results. So he ideally wants to, from a developer perspective, loss function should decrease. Or error in the prediction of the model. From an attacker perspective, the loss function should increase. Error should increase so that he can fool or deceive the model. So the developer, he will train the model so that the error or the loss function will decrease. From an attacker perspective, he makes subtle changes to the inputs. He makes, like, say for example, in terms of machine learning model to identify spam emails, right? Like the example I provided, he makes subtle changes, like small changes to the spam email so that it evades the spam filter. Okay? He makes small changes to the spam email so that it evades the spam filter. So in that particular scenario, it is a spam email, but it has fooled or deceived the spam filter, which is a machine learning model, which uses a machine learning model at the backend. Okay, for example. So the last function is increased and he has deceived the model. But in terms of developer, he will again train that machine learning model so that it doesn't miss out on any spam emails. So that is the idea behind it. And gradient is exactly used to measure, like, what changes I'm making and whether the loss function is increasing or decreasing based on the changes I'm making. Again, it is a numerical value. It is used to denote based on, like, how much the loss percentage or the loss function varies, whether it increases or decreases based on my input. Again, I will repeat again. Gradient is used to measure whether the loss percentage increases or decreases with changes in my input. Okay. And used on based on the gradients, value of the gradients, right? A developer will try to reduce the loss function during training, and based on the gradients, an attacker will try to increase the loss function. Basically, gradients is kind of like, in very simple terms, gradient is like a map. If the last, it is used to determine whether the last function is increasing or decreasing based on my input. And if the last function is increasing, the attacker will query the gradient, like basically the attacker will query the gradients of the model to increase the last function. Okay. Sorry, I'm confusing. Sorry. Basically, the attacker will query the gradients to understand whether the loss function is increasing or decreasing based on his input. Like, he will make subtle changes to the input. I will again, maybe I'm explaining too much. I will explain with this particular example. So this is an actual stop sign, image of a stop chain. This is an image of a stop chain where there are some changes. If you look closely, there are some that pixels are red, green, blue pixel values. If you see here, you would see there are some. This is the original image, but if you see the adversarial image, or the one the attacker sends to the machine learning model, right? There are some RGB pixel values. These are some deviations from the normal. Okay, this is the actual image. This is an image that the attacker has sent to the machine learning model. Okay, so he makes subtle changes. These are like subtle changes to the actual input, right? And he sends it to the machine learning model. And once he sends it to the machine learning model, he will query the machine learning he will query the gradients to understand if the loss percentage is increasing or decreasing. Based on that, he can modify the attack. If the loss percentage is decreasing, the attacker will again modify this particular image and again send it to the machine learning model. He will again query the gradients to understand if the loss percentage is increasing or decreasing. Okay, if the loss percentage is decreasing, he will again modify the input, again send it to you. If the loss percentage is increasing, actually his attack is becoming successful. If loss percentage is increasing, right, his attack is becoming successful. So he will again make some subtle changes and provides the input to the machine learning model to effectively deceive the machine learning model. So effectively, if you see this, when at the start, this image is getting interpreted as a street sign. This machine learning model is interpreting this particular image as a street sign, but the attacker has made subtle changes to the input. To the human eye, this image still looks like a stop sign because there are no drastic changes. You can see some small disturbance like this RGB pixels. You see, if you look closely, there will be some small disturbances to the original image, but this has not changed drastically. Okay, to the human eye, this still looks like a stop sign, but the machine learning model interprets it as something different. So in this case, the original machine, the machine learning model being used is ResNet 50. Here, the initial classification, right? It identifies this particular stop sign as a street sign. That is correct. But once we change, add some inputs to the original image and feed it to the model, right? It has misclassified it as a parking meter. If you see on the right side, right, parking meter. Again, if you see, this is the original street sign, and the attacker is basically injecting some data into the pixel values. Okay, changing some pixel values, and again sending it to the machine learning model. It misinterprets it as a soccer ball. Soccer ball, like that. Okay. So this is the idea behind it. So in order to understand, in order to effectively craft an attack, right? In order to effectively execute that attack, the attacker needs to query the gradients to understand whether the loss function is increasing or decreasing. Based on that, he can either reverse the changes that revert the changes he made, or he can execute the attack in a very effective way. That is the idea behind gradients. Having said that, we won't get access to the gradients in every scenario. For example, in case of proprietary models, right, we would have access only to the APIs. We won't be able to query the gradients to understand if the loss function is increasing or decreasing based on our inputs. We won't be able to get it, because most of the time we would have access to only to the APIs. We can just give it our input and understand and get the response, whether it's a, for example, whether it's a dog or a cat. We won't be able to get these numerical values in most of the scenarios. We will see attacks in both the contexts, like where if we have complete access to the model, we can query the guardians. If we don't have complete access to the model, we just have access to the API, there are other attacks we can do. We'll see in the attack phase. I think I explained it too much. I hope I did not confuse you guys. We'll see about gradients in the attack stage also, and I think you will be able to understand it better. Okay. Again, these concepts, right? Hard labels, scores, soft label, decision boundary. I will say machine learning again. Example, explain it with an example. So again, this is another machine learning model. The purpose of this machine learning model is to predict whether the final price, is affordable or expensive. Again, this particular machine learning model will take in multiple inputs like the 2 BHK, 3 BHK plot area and other things. And finally, it will predict whether the house is affordable or expensive. So in this scenario, it is not going to predict the price, but it will predict whether the house will be affordable or expensive. So only there are two answers. And we call these affordable and expensive as class labels. for this particular scenario. Another example of a class label would be dog, cat, apple, oranges, or anything, right? So these class labels are the final answers of the model. Class label would be affordable or expensive. So this is the final answer of the model. Okay, based on the inputs that we receive, the final answer of the model will be either affordable or expensive. Okay, so we call these terms as class labels. So hard label is the final answer, the final label answer of the model. Okay, whether it's a cat or a dog, that is the final answer of the model. That is the hard label. Scores and soft labels are like quite similar. So the model has received multiple inputs, right? Based on the inputs that it has received, it will give some probability values. Affordable, it will give some 0.7, and expensive, it will give 0.3. So out of 100%, right? So it will give some, it will assign some probability value. Like it is confident. That means to say, it is confident that machine learning model is confident that but this particular house is affordable. So it will assign a probability value to that, to that particular class label. Okay? So that means it signifies the confidence that the machine learning model has on this particular class label. Okay, so it gives a probability value called which denotes to 70%. Expensive. So it, like, even though it is it is little confident that it is an affordable house, it is also little confused. There is a probability that 30% it could be inexpensive. So it assigns this particular probability distribution to the class label, expensive class label. So these probability values are the soft labels, are the scores. Soft label is the scores are like numerical outputs of the model. Once it is converted into probability, it becomes a soft label. So these are probabilities. 0.7 and 0.3 are probabilities. So we call it as soft label. Most of the time, as I mentioned, right, in an actual attack, most of the time you would have access only to the hard labels, the final answer of the model. You won't have access to the scores also. Like in certain scenarios, we might have, if we have certain access to the model, we would have, we can query the model to understand the scores it assigns to the class labels, or the soft labels it assigns to the class labels. But most of the time, we would have access only to the hard labels. Okay. And the decision boundary is like an imaginary line that what I can say, um, partitions this class label actually. Like here, there are two class labels, right? One is affordable or expensive. So it's an imaginary line separating the two class labels. These terms will be useful when we come to the attack phase. Like right now, it could be vague, but these terms are useful in an actual attack. So in an actual attack, as I mentioned, right, this decision boundary is like an imaginary line separating the class label. From an attacker perspective, if he wants to cross misclassification, right, he will try to cross this imaginary line, the decision boundary, so that he can deceive the model and cause misclassification. That is the idea behind the term called decision boundary. From an attacker perspective, if he wants to deceive the model or he wants to cause misclassification, right, he will try to jump the decision boundary or cross the decision boundary, so that the actual, say for example, in terms of an image classification, a dog gets misclassified as cat. So that is the ultimate aim from attacker perspective. Coming to the actual attacks, so these are certain this particular class of attacks, right, targets classification based models. To give examples, like for example, in using this particular attack, we can evade a spam filter or a machine learning model used for a malware identification by EDRs, for example, right. To give a very accurate example, like we would have seen that example multiple times during this, like I would have mentioned it multiple times. There is a machine learning model used for image classification or object classification. Okay, you give it an input, okay, and the model classifies it as a particular object or a particular animal or a particular fruit or something like that. So you make changes to the input image. Okay, you make subtle changes to the input image. From an attacker perspective or a human eye perspective, the image will remain the same. Okay, so from a human eye perspective, the image will remain the same. There won't, because we are making only subtle changes to the original image, but the model will misclassify it. So this has its significance or effects in, for example, facial recognition systems or autonomous driving. Say for example, in facial recognition systems, they use an image classification model at the back end, right? So if we can deceive the model to cause misclassification, then we can evade the facial recognition systems. Or in terms of autonomous driving, say for example, researchers in this particular scenario, I would have mentioned a particular research article here. Researchers proved that like state of the art, so state of the art object detection machine learning models, right, failed to recognize stop signs once they covered the stop signs. So they conducted this attack in an actual environment on the road, right, in a real time scenario. On the road, they conducted this attack. So what they did was, on the stop signs that are on the roadside, right, they stuck some posters or adversarial images, like they stuck on top of the stop signs, right? They stuck some posters or stickers on top of the stop signs. Okay, from a human eye, again, from a human eye perspective, okay, the image will remain the same. From human can once a human sees that stop sign, right, he can immediately recognize that it is a stop sign. This particular poster or the sticker that is stuck onto the stop sign is not um, it is not immediately recognizable by a human, from a human eye perspective. But the machine learning model will interpret that particular sticker or poster that was stuck onto the original object, right, the stop sign poster. In this scenario, it will either misinterpret it, or it will stop like in this scenario, what it what happened was, this object detection model failed to recognize the stop sign itself. Okay? In this scenario, the object detection model failed to recognize the stop sign itself, because these researchers, they embedded or attached adversarial posters or signs on top of the stop signs. Okay. So this is an example, real-time example of a model evasion attack. Again, it has its implications. Again, I would mention, like, it has its implications in multiple areas, like facial recognition, spam filters, malware detection, and autonomous driving. We will, or like, once we go to the POC, right, we will have a better clarity, like how the attacker actually executes this attack. We would have studied about the gradients and all these things, right? Hard labels, soft labels. So that is because we have, like, what kind of attack we are going to do in model evasion, right? There are two different kind of categories. One is like, if we have complete access to the model, where we can query the gradients. I would have mentioned, right? Where if we have complete access to the machine learning model, we can query the gradients to understand if our loss function is decreasing or increasing based on our input. Okay. If you don't have access to the machine learning, complete access, if you don't have complete access to the machine learning model, there are certain other attacks that we can do. Like, for example, if we have only access to the confidence store, there are certain algorithms that we can use. Or if we have access to the only to the final answer, which are hard labels, whether it is a cat or a dog, right? Based on that, we can execute certain attacks. I will see, like, in case of open box, where we have a complete access to the model, right, we can query the gradients. I would have mentioned, right, we can query the model's gradients to understand what an attacker will do, right? He will take an input image, like, for all these examples, right, we can take an image classification model as an example. We are going to input images to the model. Okay, we are going to send only the images as input to the model, okay, for understanding purpose. So the attacker will take an image, okay, say for example, image of a dog. So he will add some subtle changes to the image. Okay, he will replace some pixel values. He will make small changes to the images, and he will feed it to the machine learning model. Then he will, since he in this particular attack, since he has complete access to the machine learning model, he will query the gradients. So he has made some changes to the input image. He sends it to the machine learning model. Then he queries the gradient to understand if the loss function is increasing or decreasing. Okay, if the loss function is decreasing, okay, ideally from an attacker perspective, loss function should not decrease. Okay, so what he will do, he will revert the changes. Whatever changes he has done to the input, right, to the image, right, he will revert the changes. Okay, he will make some other changes. He will replace some other pixel values. Okay, he will make some other changes to the input image, and then he will again send it to the machine learning model for inference, and again he will query the gradient, okay, to understand if the loss function is increasing. If the loss function is increasing, now he's going in the right direction. That means he is going in the right direction. This is eventually going to cause a misclassification. Again, you make some subtle changes to the input. I will explain it with the flow instead of explaining orally, right? Uh, Attacker, small changes to the input image, sorry, submit it to the model for image classification. Okay. Vary the gradients. Loss function is decreasing. Revert the changes because the attack is not successful. He will again make changes. Vary the gradient again. Check if loss function is increasing. If it is increasing, this is the right direction to deceive the model. Okay. Repeat the above steps. Understood, right? Like he will make changes to the input image, submit it to the model, vary the gradients to understand if loss function is increasing or decreasing. Based on that, he will either revert the changes, make some other changes, and submit it to the model again. And if the loss function is increasing, it means the attack is getting better. Better. There is a possibility that attack might be successful, and he has to go in that direction. And he will repeat the above steps again, so that he can the changes that he has made to the image is subtle, and also the model misclassifies it. So he will reiterate these steps again and repeat these steps again and again until the attack is successful. So this is the idea behind gradients, loss function, everything. This is possible only if we have complete access to the model. So in this scenario, if we have complete access to the model, then we can use certain algorithms developed by researchers. Like there are multiple algorithms. I would have mentioned some algorithms here, which is Carlini, Wager, and fast gradient sign method. On the internet, there will be like multiple methods related to model evasion. There is another algorithm called as a projected gradient descent attack, something like that. If you see on the internet, there are multiple attacks, multiple blogs on how to execute these attacks with images with the state of the art machine learning models, right? So that you can see multiple blogs on how to use these algorithms to deceive a machine learning model. There will be blogs on fast gradient side method, projected gradients descent method, I suppose, where they will take this attack is quite famous actually. That most of the time you would have seen, like they would have taken an image of I think polar bear, make some subtle changes to it, submit it to the model until the model misclassified it as something different. To the human eye, that image of a polar bear will remain the same. Okay, if to the human eye it still looks like a polar bear, but the model will misclassify it as something different. That is the idea behind model evasion attacks. Okay. In closed box attacks, as I mentioned, most of the time we won't have access to the gradients to carry the loss function, to understand the loss function. Okay. In those scenario, we will have only access to the probability scores, like how the confidence that the machine learning model has on a particular class label. Or let's say, for example, if it feels that this is an image of a dog, right? It give a probability like 80%. Just for an example, okay, 80%. If it feels that this is an image of a cat, it will give a probability like 20%. So if we have only access to this probability scores, right, then we have to use certain other algorithms to execute these attacks, which are like square attack and zeroth order optimization attack. Okay, we will see like one particular demo with the hop skip jump attack, like with the demos. The next slide, we'll see the demo with the hop skip jump attack. But yeah, under different scenarios, right? There are different algorithms to execute the attack in an effective way. But the idea is, right, we have to receive the machine learning model, and also we have to make very subtle changes to the machine input image. So from a human eye perspective, it still remains the same, but a machine learning model will misclassify it. So that is the idea behind all these algorithms. These algorithms will have its advantages. Some of the these algorithms will send multiple queries to the machine learning model. Some of these algorithms will solve the will basically execute the attack in lesser time, like within few minutes or within some 100 queries or something. Some algorithms take 1,000 queries or an hour to execute the attack. It depends. And also it depends with the access we have, whether we have access to the gradients or we have access to only the confidence cores, which are the probability outputs. Now coming to the last section, which is hard labels. So most of the time, as I mentioned, we would have only access to the API. We won't have access to the gradients, or we won't have access to the probability scores. So we would have access to the only the hard label. So if we give it an image and the model says this is an image of a cat, so that is the only answer that we get from the model. We won't have access to the probability percentage. We cannot query the gradients to understand the loss function. We cannot do anything. Even in this scenario, we can execute model evasion attack, and using an algorithm called hop skip jump attack. Actually, we'll see about this particular method. So in hop skip jump method, what they will do, right? So we'll say cat. We take two images and not a cat. So basically, we take an image of a cat, and we can take any other image which is not a cat, like a dog or a tractor or a panda or anything, right? So we take an image of a cat, and we take another image which is not a cat, okay, and we feed it to the machine learning model, and the model classifies it as a cat, okay. So this is the initial output. So what hop skip jump does, right? It uses different algorithms like binary search and different mathematical functions, like for example, geometric progression. So it uses different algorithms to to effectively identify a point where the model misclassifies it as not a cat. Okay. Previously we would have discussed about decision boundary, right? Decision boundary, an invisible line separating the class labels. Okay. So here we have two scenarios, which is like cat and not a cat. And just imagine, like decision boundary is like an imaginary line that is separating the model's decision, whether it's a cat or not a cat. So that is the model decision, and the decision boundary is an imaginary line separating these two class labels. Okay. So here we use binary search to identify a point near the again, this is a mathematical algorithm, right, which is used to find a point near the decision boundary. Okay. Once using binary search, once we have identified a particular point near the decision boundary, we make changes to the input. We make changes to the cat image. Okay, we send it to the machine learning model, and then query what is the answer from the model. Here we don't have access, as I mentioned. This is a, I would say, from a black box perspective, this is like a black box attack, right? So here we cannot query the gradients, we cannot understand the loss function, we don't have access to the probability outputs. We just have we just get only one answer, whether it's a cat or not a cat. We can get only this answer from the machine learning model. Okay. So using binary search, we have identified a point near the decision boundary. Okay. Then what we do, right? We make subtle changes to the image of the cat. Okay, and then send it to the model and get the answer. So the answer will be either a cat or not a cat. And based on that, we assume the gradients, we assume the direction. Okay, this is an assumption. Here we won't be able to query the gradients because we don't have complete access to the model. Okay, here that we assume the gradients, we make changes to the image, we send it to the model, and based on the answer, whether we will revert the changes or make more changes to the, like this in the previous scenario I mentioned, right? If based on the answer, we are querying the gradients, but in hop skip jump attack we cannot query the gradients because we don't have access to the model. Okay, but based on the answer of whether it's a cat or not a cat, we either revert the changes or make more changes to the input, and again send it to the machine learning model to understand whether the model is misclassifying it or not misclassifying it. Again, as I mentioned, right, it uses binary search and geometric progression to make changes to identify the decision boundary, get closer to it, right? Get closer to it, and it will iterate the steps again and again. It will um, it will try to find a point, make changes to the input, submit to the model, check the class label whether it's a cat or not a cat. Based on the answer, it will either revert the changes or try to make more perturbations or more changes to the input, and it will try to get to the decision boundary as much as like it will try to get close to the decision boundary as much as possible. And again, it will repeat all these steps again and again in an iterative manner until the attack is successful. That is the idea behind this hop skip jump attack actually. So it will repeat all these steps. The step one, the binary search. Second two is to estimate the gradient at the identified point using binary search, right? There was a point identified. So it will estimate the gradient, and then based on the answer from the machine learning model, it will try to close into the decision boundary, and it will iterate the steps again and again until the attack is successful with subtle changes to the input. So instead of a theoretical explanation, we'll go to the attack demo itself. And there is a concept called as L2 and L infinity similarity norms. We will discuss about in the actual attack actually. So here we are going to use TensorFlow, and there is a particular Python package for implementing this particular attack. So this is the package. So already multiple researchers have done analysis on this particular field, and they have created this particular Python package for executing this attack. So this within this particular repo, there are they hold resources for evasion, poisoning, inference, extraction related attacks, as well as they have given defense for the blue team, defense tips on how we can prevent these attacks. Defense tip from a blue team perspective, right? They have given defense tips also. There are multiple research papers associated, like they have mentioned, referenced within this particular repo. If you're interested, you can go through the entire repo. This is like a vast repo. It has details on multiple different attacks, multiple different research papers. And they have given a Python package also, which we can import in our code, like in our Python code, and easily like implement the attack. For example, for hop skip jump, right, there is a research paper. You see, we would have referenced the research paper for this particular hop skip jump attack. Again, the hop skip jump attack itself has a own GitHub repo. Okay, if you want to use, you can use that GitHub repo also for executing the hop skip jump attack. But what they've done, this particular repo, right, they have taken all these attacks, they have created a Python library so that we can implement it. We don't have to like write the Python code from scratch for executing this algorithm. Okay, they have implemented this algorithm in their own package. We can just import this algorithm as a function within our Python code. We don't have to implement the algorithm from scratch. We don't have to write the algorithm from scratch. Okay, so they have already implemented it within their Python package. We are just, so to execute hop skip jump attack, we are just going to call the hop skip jump attack function. That's it. We are going to import this package, and we are going to just call the function. So as I mentioned, we're going to use TensorFlow, and from here, if you see adversary, I think robustness, right? Robustness toolbox. We're going to import the package, okay? And these are like unnecessary. Like I'm just going to run it on macOS MPU, just for faster processing and inference and everything. Actually, as I mentioned, we are going to use a existing model. Okay? We are going to use an existing model, which was once a state of the art model, which is called as ResNet 50 model. This was introduced by Microsoft. This is a model that is explicitly used for image classification. This is a machine learning model that is explicitly used for image classification. Okay, so we are going to using TensorFlow, we are going to load this model, and we are going to submit our images to this model for classification. Okay, in the first, if you see on the left hand side, these are the original predictions of this ResNet 50 model. Then what we'll do, right, on the images. So on my laptop, I have this particular folder, stop signs too. So here I have 10 images of different stop signs. 10 images of different stop signs. All are stop signs only, but different taken from different angles, different images. Okay. So if you see 10 different stop sign images. Okay, so I have this folder. So I am going to give this to the ResNet 50 model for classification. So once it has come, this is the initial classification of the ResNet 50. Everything you see on the left side, right? So this is the initial classification of the ResNet 50 model. Then we are going to make some changes to the input image, the stop sign, right? Using hop skip jump algorithm. So we are going to implement hop skip jump algorithm, and using that algorithm, we are going to make some subtle changes to the input image. And then again, we are going to, this is the adversarial image. So this is the original image. On the right hand side, everything that you see on the right hand side is the adversarial image. So we are going to give the adversarial image to the, again to the same ResNet 50 model, and see how it classifies. That is the idea behind this Jupyter notebook. So maybe I have run it again, but I will run it again. I just ran it like 15 minutes back, but I will run it again. I saw some warnings. Okay, I think it was reloaded. Sorry, just give me a minute. Okay. So we are going to take in all the images from this particular folder and going to give it to ResNet 50 for classification. We will do some basic editing, like pre-processing. Basically, we feed it to the machine learning model in a particular size, right? So we do some basic pre-processing or editing the images before we feed it to the machine learning model. Now we are going to execute the hop skip jump attack. If you see, I'm just importing a function, using a function that comes with the art library, Python library. I'm not going to implement a hop skip jump from scratch. Okay? I'm just going to use the function that is already provided by that library. Okay, and we are going to, like I mentioned, right, this binary search and the gradient estimation and moving closer to the decision boundary. These are done iteratively again and again, right? So here we are doing 3 iterations. See, 3 iterations. We're doing, like, we can increase the iteration to make sure the attack is very effective, but time constraints and other things like device constraints and all, like we have limited it to 3 only. But you can increase the iteration step to make the attack more effective. Okay. Now hop skip jump is attack is executing. Let's wait, like I think it will take 2 minutes.
Yeah, bro, I have a question.
Yes,
So, you previously had you are loading the images from a directory,
yes,
but are they only are they the original images, right?
yes.
They are the original images. They are not alterated images.
No, no. They are the original images that I think I took it. Sorry, I took it from Calset, some data set called as Calset, I believe.
Okay, okay,
There are
understood.
different data sets like ImageNet, uh, Cipher, something like that. So I took it from a particular data set in the internet. Since like we don't have the machine capabilities or like a time to go through an entire data set or load it remotely, right? Like if I'm loading
Hmm.
it remotely, there will be like it will be in terms of MBs and GBs. So I just took 10 images from my original data set. Those are unmodified images.
Okay, got it. And also, I have a question for loading this ML model.
Okay.
In the second block or third block, you are loading it like just like a function
Yes.
with Terraform with TF. So that's how we do it, right?
Yes. Yeah. Exactly. Using TensorFlow. Exactly.
Okay, okay,
I'm loading it at
okay,
the Mac GPU, like Mac OS MPU.
okay. It will basically fetch it from a repository, I assume.
I think so. Comes pre-built. I think so.
Okay, okay.
Okay. Now the hop skip jump attack is executed. Okay. Now we are going to submit both the original image and the adversarial image. Right now, if you see, the L2 distance, if you take notice of this the L2 distance, right? It is in terms of a 4-digit actually. If I run this attack again, like as I mentioned, right, I executed this attack like 1 hour before. Now the L2 distance is something like 3074 or 6066. If I execute this attack again, this will change actually. If you see now, this might change. If you see, initially it was like 3704 something like that and 66 something like that. If you see, the L2 distance has changed actually right now. Now, as I mentioned, this is the left side. This is the original image. On the right hand side, this is the adversarial image. Okay. If you see, the original prediction is street sign, except for the last image. Again, it's a stop, but the resonant model classified it as a gas mask. I don't know. Now we have executed the hop skip jump attack, and we are feeding this adversarial image. Like if you see from a human eye perspective, it like if you look closer, there are some subtle changes. If you see here and all, there are subtle changes. If you look closer, but from a human eye perspective, it still remains the same. Like it is a stop sign only. It is not drastically different, right? It is a stop sign only. Humans can interpret it as a stop sign, but the machine learning model interprets it as a soccer ball. Here, parking meter. Here in this particular, the attack failed. In this for this particular image, right, the attack failed. The hop skip jump attack failed. Basically, it was not able to find the decision boundary. It was not able to perturb or make changes to the images so that the model classified it. Because as I mentioned, right, we ran only 3 iterations of hop skip jump attack. Okay, we haven't run multiple iterations. If you run like 10 or 20, there might be a possibility that the algorithm can fool the machine learning model. But in this, since we ran only 3 iteration, for this particular image, hop skip jump was not able to find a point or a decision boundary where it can fool the model or deceive the model. So if you see here, the adversarial image is street sign only. So the attack was not successful only for this particular image. Again, for this particular image, it identifies as a bottle cap, spatula, rubber eraser. L2, I mentioned L2 distance. L2 distance, again, a numerical value. It measures how dissimilar the adversarial image is from the original image. For example, if you see L2 distance that is in 4-digit, right? It is like very dissimilar. Like it is like the perturbations are more like it is, I would say, like it is not exactly the same as the original image. Okay, if you see here, this is the original image. Here the L2 distance is in terms of 5-digit. You can see the inputs, like what I can say, perturbations or basically the modifications that the attacker has done, right? This is like very dissimilar to the original image. So L2 distance is used to measure that similarity. Okay, so this is in terms, this particular value is in terms of 5-digit, right? You can see like it is like very, it is not the original image. There are multiple dots on it. I would say this attack
Kind of noises.
yeah, kind of noises. Sorry. Thanks for that. That was the word I was thinking. I wanted to mention actually. Kind of noises. Okay. So the noise is more here. We see here, and the noise is more. From a human eye perspective, we can see like there are many noises here. There are multiple modifications here. I would say even though the model misclassifies it, right? I would say the attack is not effective because there are multiple noises here. It is not very similar to the original image. Okay. But if we run multiple iteration, maybe the L2 distance will get shorter. It will be like in 3 digits or 2 digits. It will be the adversarial image like it will be very similar to the original image in terms of noises. We won't be able to visually see the noises. Okay, it will be very similar to the original image, but the attack will become successful. The model will misclassify it. For example, here if you see the L2 distance is 346, 3 digits only, and it is misclassifying it as a rubber eraser. Okay, it is very similar to the original image. We don't see many noises here. Okay, but the model misclassifies it as rubber eraser. But here, if you see the L2 distance is in terms of 4-digit, it is dissimilar, or like the noises are more. Like if you see the noises are more, like it is slightly the brightness is less. There are many modifications to the original image. So the L2 distance is 4567 in terms of 4-digit. So L2 distance is used to measure the similarity of the adversarial image from the original image. It would be better if the L2 distance is in terms of 2 digit or 3 digit, so that the adversarial image is like very similar to the original image, but the model also misclassifies it. That is the idea behind these attacks. Okay, so now this is the with this we are closing a model evasion attack. Any doubts on model evasion attacks? I will stop here. Like any doubts that you have on model evasion attacks. One more thing I wanted to include, like as I mentioned, right, there are multiple demos with image-based classification, right? But ideally, I would try with something like spam-based machine learning model, or the machine learning model that is used to identify spams, or a machine learning model that is used to identify malware. I will check if there is any machine learning model that is openly accessible that we can try implementing in our Jupyter notebook, that we can try bypassing, and that will be more impact. I would say that would be more interesting actually. But this attack on image-based classification model also has its impact. As I mentioned, this could impact facial recognition systems. This could impact autonomous driving, right? The machine learning models for autonomous driving. So this is the impact that can cause this particular attack will affect those, has its impact on those fields also. But when it comes to cybersecurity, say for example, I can try with something like a machine learning model used to identify spam, or machine learning model used to identify malware, right? We'll see if anything is available, if we can try, and we'll let you know if I can do it and it becomes successful. I will post it in the WhatsApp group actually. And there was some research associated with model evasion attack on IDS actually. So there are multiple research associated with machine learning models related to IDS, as I mentioned, is spam, network security. In this case, network security, spam, or malware detection, right? So this model evasion attacks is applicable not only on image classification models, but also it is applicable to multiple different fields, like in this case, IDS. Okay, I will stop here. Like for this particular class of attacks, model evasion attack, if you have any doubts, let me know.
ஓகே, யாரும் கொஸ்டின்ஸ் இருந்ததுன்னா நீங்க அன்மியூட் பண்ணி கேட்கலாம், தமிழ்ல கூட கேட்கலாம்.
யா, உங்களுக்கு கேட்கணும்னா டைரக்டா கேளுங்க. யா,
ஆமா. ப்ரோ, இப்போ எனக்கு ஒரு கொஸ்டின் இருக்கு சார். நம்ம இப்போ இந்த மாதிரி இந்த அர்கைவிக்ஸ்ல எல்லாம் பேப்பர்ஸ் பாக்குறோம் நிறைய.
ஆமா.
பட் வந்து நம்ம அர்கைவிக்ஸ் ஓபன் பண்ணோம்னா அதுல கண்ணாபண்ணா நிறைய பேப்பர் வருது. ஏதாவது வந்து ஒரு என்ன சொல்றது, சம்திங் வந்து அதை கிளாசிஃபை பண்ணி நல்ல பேப்பர்ஸா எடுத்து வைக்கிற மாதிரி, இல்ல வந்து அது மாதிரி எதுவும் நியூஸ் லெட்டர் இல்ல அந்த மாதிரி வெப்சைட் அந்த மாதிரி எதுவும் ஐடியா இருக்கா உங்களுக்கு?
இல்ல,
நீங்க எப்படி பாக்குறீங்க இந்த பேப்பர்ஸ் எல்லாம்?
இல்ல, நான் இப்போ அதுல போயிட்டு ஃபில்டர் மாதிரி போட்டு தான். நம்ம அதுல ஃபில்டர் எப்படி இருக்கும்னா, டைட்டில் வச்சு சர்ச் பண்ணலாம், ஆத்தர்ஸ் வச்சு சர்ச் பண்ணலாம், இல்லாட்டி கண்டென்ட் வச்சு சர்ச் பண்ணலாம், அந்த மாதிரி தான் இருக்கும். நான் டைட்டில் அண்ட் அந்த ஆப்ஸ்ட்ராக்ட் இருக்குல்ல, இந்த ஃபர்ஸ்ட் பேராகிராஃப் அப்ஸ்ட்ராக்ட், இதை வச்சு சர்ச் பண்ணி தான் எடுத்தது ஆக்சுவலா.
ஓகே,
எக்ஸாக்டா ஸ்பெசிஃபிக்கா தெரியல. இந்த அப்ஸ்ட்ராக்ட் இந்த டைட்டில் வச்சு தான் எடுத்தது. ஏன்னா இது மட்டுமே இல்லை, நிறைய ஆர்டிகல்ஸ் இருந்தது. நிறைய பேர் இந்த பர்டிகுலர் இதுல ரிசர்ச் பண்ணி போட்டிருக்காங்க. அதாவது ஒருத்தவங்க என்ன பண்ணுவாங்கன்னா, இதை அவாய்ட் பண்றதுக்கு, இந்த மாடல் எவேஷன் அட்டாக்ஸ் அவாய்ட் பண்றதுக்கு ஒரு பேப்பர் போடுவாங்க. அந்த பேப்பர் ஒர்க் ஆகாதுன்னு சொல்லி இன்னொருத்தவங்க ஒரு பேப்பர் போடுவான். அந்த டிஃபென்ஸ் ஒர்க் ஆகாதுன்னு சொல்லி இன்னொருத்தர் பேப்பர் போடுவோம், இந்த டிஃபென்ஸை பைபாஸ் பண்ணலாம் அப்படின்ட்டு. அந்த மாதிரியே எக்கச்சக்கமா இருந்தது இந்த இதுல.
இல்ல, அதுதான் ப்ரோ பிரச்சனை. நிறைய இருக்கு, எல்லாத்தையும் படிச்சு புரிஞ்சுக்க முடியல, கஷ்டமா இருக்கு. என்ன கீவேர்டு போறதுன்னு தெரியல சம்டைம்ஸ். ரைட், இப்படி ஒரு அட்டாக் இருக்கானே நமக்கு தெரியல. அப்படி கீவேர்ட்ஸ் போடுறதும் கஷ்டமா இருக்கு. எல்எல்எம், எம்எல் அந்த மாதிரி ஜெனரிக்கா போடுற மாதிரி.
புரியுது. ஆமா,
அதான் இஷ்யூ.
நீங்க கேட்டதுக்கு அதுதான் என்னன்னா, இது அப்படியே ஒரு பைத்தன் பேக்கேஜ் அப்படியே ரெஸ்னட் ஃபைனைட் இது நம்ம லோக்கலா லோட் பண்ணல, அது பேக்கேஜ்ல இருந்து லோட் பண்றோம். ஐ திங்க் என்னோட கெஸ் என்னன்னா, இட் வில் புல் ஃப்ரம் தி இன்டர்நெட் அண்ட் லோட் இட் இன் தி பேக்கெண்ட். அப்படிதான் நான் என்னோட கெஸ். இது ஆக்சுவலா பேக்கேஜ்ல அப்படியே நம்ம ஃபங்க்ஷனலா லோட் பண்ணிடுறோம். ஆனா இது லோக்கல் மாடல்.
ஓகே, சரி, இது டாக்குமெண்டேஷன் படிச்சா தெரியும் ப்ரோ. பட் ஃபைன். ஆக்சுவலா ரொம்ப தேங்க்ஸ். ஆக்சுவலா இப்போ என்னன்னா, நானே இப்போதான் ரீசெண்டா வந்து ஒரு இந்த ரெப்பலோ ஏயோ ரெப்டல் ஏயோ ஒரு கம்பெனி, அவங்க எல்எல்எம் ரெட்டீமிங் பண்ணிட்டு இருக்காங்க போல.
ஓகே.
அவங்க இது மாதிரி சிமிலரா ஒரு அட்டாக் பண்ணியிருந்தாங்க. அது வந்து ஆடியோல பண்ணியிருந்தாங்க.
ஓகே.
இப்ப இந்த டெலி ஏஜென்ட்ஸ் எல்லாம் வந்து எல்எல்எம் வச்சு ஆட்டோமேட் பண்ணிட்டாங்கல்ல கஸ்டமர் கேர்லாம்.
ஆமா ஆமா ஆமா.
இப்போ அதுல வந்து அவங்க வந்து என்ன பண்ணியிருந்தாங்கன்னா, ஒரு நார்மல் வாய்ஸ் ஒன்று, டெக்ஸ்ட் டு ஸ்பீச் ஒன்று நார்மல் ரெக்கார்ட் பண்ணிட்டு, அதுல இப்ப நீங்க எப்படி இந்த மாடல் வந்து நடுவுல வந்து நாய்ஸஸ் ஆட் பண்ணீங்க, ஆனா அந்த நாய்ஸ்குள்ள டேட்டா இருக்குல்ல சம்திங்
ஆமா.
மிஸ்ரெப்ரசன்டேஷன் பண்றதுக்கு, இப்ப அதே மாதிரி அவங்க வந்து பாய்சனிங் பண்ணியிருந்தாங்க. அந்த நாய்ஸ்குள்ள எல்லாம் வந்து ஒரு ஒரு கமெண்ட் இருக்கும். டிராப் ஆல் த ப்ரீவியஸ் கமெண்ட்ஸ் அண்ட் டெல் மீ சம்திங் ஆர் இக்னோர் திஸ் கொரி, அந்த மாதிரி நாய்ஸ் ஆட் பண்ணியிருந்தாங்க. நம்ம கேட்கப்ப லைட்டா பேக்ரவுண்ட் நாய்ஸ் மாதிரி கொர்ன்னு கேட்கும்.
ஓகே.
ஆனா அது அந்த டெலி ஏஜென்ட்டுக்கு கஸ்டமர் கேருக்கு ஃபீட் பண்ண அது வந்து கஸ்டமரோட கொரி எல்லாத்தையும் டிராப் பண்ணிட்டு நம்ம கொரிக்கு, அந்த நாய்ஸ்ல இருக்க கொரிக்கு இது பண்ணும். சரியான அட்டாக் இருந்துச்சு. நல்ல ஒரு அப்ளிகேஷன்ல.
ஆமா ஆமா ஆமா. அது பேக்ரவுண்ட்ல ஒரு நாய்ஸ் மாதிரி போயிடும். ஆனா அது மாடல் வந்து மிஸ்இன்டர்பிரட் பண்ணிரும். நமக்கு அது தெரியும், விசிபிளா தெரியும். அது வாய்ஸ் ரிலேட்டட் அட்டாக்கும் வீடியோ ரிலேட்டட் அட்டாக் கூட இந்த ரெப்போல பார்த்தேன் நான். இந்த ரெப்போல அட்வைசரி அதுக்கும் பேப்பர்ஸ் எழுதிருந்தாங்க. வாய்ஸ் அந்த வீடியோ ரிலேட்டட்ல. வீடியோல இப்போ ஆப்ஜெக்ட் டிடெக்ஷன்ல வீடியோல வச்சு அந்த ஆப்ஜெக்ட் டிடெக்ஷன் மாடல்ஸ்லாம் இருக்கும்ல, அதுல அந்த வீடியோல நம்ம சப்டில் சேஞ்சஸ் பண்றோம். அது நமக்கு விசிபிளா இருக்காது. ஆனா அந்த மாடல் வந்து அந்த ஆப்ஜெக்ட் ஒன்னு அது ஐடென்டிஃபை பண்ணாது, இல்லாட்டி வந்து மிஸ்இன்டர்பிரட் பண்ணிக்கும். ஐடென்டிஃபை பண்ணிக்கும்.
கரெக்ட்.
அதேதான் அந்த வாய்ஸ் நீங்க சொன்னீங்கல அந்த ஆடியோ மாதிரி தான். அதே மாதிரி.
இல்ல நமக்கு ஃபியூச்சர்லயே மேபி வந்து நம்ம ஒர்க் வந்து இப்படி மாறலாம். அதுக்கு நிறைய வாய்ப்பு இருக்கு. நம்ம சும்மா அப்ளிகேஷன் பென் டெஸ்டர் இல்ல ப்ராடக்ட் செக்யூரிட்டி இன்ஜினியர் கண்டிப்பா ப்ராடக்ட்ல ஒரு ஏஐ இருக்கும்.
ஆமா.
அதை டெஸ்ட் பண்றதுக்கு யூஸ் கேஸ் எடுத்துட்டு வரக்குள்ள நம்ம வந்து இந்த 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 மாதிரி எவேஷன்ஸ் எல்லாம் பண்ற மாதிரி இருக்கும். கண்டிப்பா.
ஆமா கண்டிப்பா கண்டிப்பா.
எல்லாத்துலயும் இன்டகிரேட் பண்ணிட்டாங்க. எல்லா கம்பெனியும் ஒர்க் பண்ணிருக்காங்க.
ஆமா. ஸ்பாம் ஃபில்டர்லாம் நல்ல யூஸ் கேஸ். இப்ப சாக்ல எல்லாம் நிறைய முன்னாடில இருந்து எம்எல் இருக்கு, இப்ப எல்எல்எம் எல்லாம் இது பண்றாங்க. இப்ப வந்து நம்ம வந்து லாக பாய்சன் பண்ணோம் அப்படின்னா நீங்க இப்ப இமேஜ்ல பண்ற மேட்டர் அங்கேயும் வரும்.
ஆமா எக்ஸாக்ட்லி. இன்னொன்னு என்னன்னா இந்த ஏஐன்னு சொல்றேன், ஜெனரேட்டிவ் ஏஐ புரியுது. ஆனா நீங்க நிறைய ப்ராடக்ட்ஸ் பாத்தீங்கன்னா முன்ன நான் 10 இயர்ஸ் முன்னாடி நான் ஐடி ஜாயின் பண்ணும்போது மிஷின் அந்த இடிஆர் ஆன்டிவைரஸ் பத்தி எனக்கு சொல்லும்போது மிஷின் லேர்னிங்லாம் இருக்குப்பா, அதெல்லாம் எல்லாத்தையும் கண்டுபிடிச்சிரும் அப்படின்னாங்க. ஓகேங்களா? மிஷின் லேர்னிங் அதே இதை இப்ப கொண்டு வந்துட்டு எனக்கு ஜெனரேட்டிவ் இந்த அந்த செக்யூரிட்டி ப்ராடக்ட்ல ஜெனரேட்டிவ் ஏஐ இருக்குப்பா, இது எல்லாத்தையும் கண்டுபிடிச்சிரும்பா அப்படின்னு அதே இதை விற்கிறானுங்க.
அது ஒன்லி மார்க்கெட்டிங் ப்ரோ, அவ்வளவுதான். ஒன்னும் இல்ல,
அந்த டேர்ம் மட்டும் தான் வருது. ஆனா மிஷின் லேர்னிங் தான்.
ஹலோ கேக்குதா?
சொல்லுங்க ப்ரோ.
ஜான் ப்ரோ, நீங்க ஒரு அட்டாக் சொன்னீங்கல்ல, லைக் எனக்கு கேக்கல, டக்குன்னு வெளியே போயிட்டேன். நான் இதுல இருந்தேன், லேப்ல இருந்தேன். ஏதோ ரெட்டிமிங் 2 ஏஐ மாடல் வச்சு ஏதோ பண்ணீங்க சொன்னீங்களா, லைக் அதை ஒரு டைம் ரிப்பீட் பண்றீங்களா?
அரவழி ப்ரோ தானே, ஆடியோ தானே கேக்குறீங்க?
ஆடியோ ரிலேட்டட் ஏதோ அட்டாக் சம்திங்.
ஓகே ஓகே, நான் எக்ஸ்பிளைன் பண்றேன். அது ஒண்ணும் இல்லை, லைக் ரெப்பலோ ஏயோ ரெப்டல் ஏயோ ஒரு எல்எல்எம் ரெட்டீம் பண்ற ஒரு கம்பெனி தான், இந்தியன் பேஸ்ட் கம்பெனி தான். அவங்க பேசிக்கலி என்ன பண்ணியிருந்தாங்கன்னா, இப்போ நம்ம செஷன்ல வந்து மணிப்ரோ வந்து இமேஜ்ல பர்டிகுலர் நாய்ஸஸ் ஆட் பண்ணி எம்எல் மாடல்ல கன்ஃபியூஷன் பண்ணியிருந்தாரு. இதே சிமிலர் அட்டாக் வந்து அவங்க வந்து வாய்ஸ்ல பண்ணியிருந்தாங்க. வாய்ஸ்ல நமக்கு வந்து இப்ப இந்த கஸ்டமர் கேர், இந்த டெலிகாலர்ஸ் எல்லாம் வந்து இப்ப எல்லாமே நிறைய எல்எல்எம் ஆயிடுச்சு. ஆமா ஆமா. சோ இப்ப அந்த இதுல எல்லாம் வந்து இவங்க வந்து பேசிக்கா ஒரு கஸ்டமர் கொரிய வாய்ஸ் டு டெக்ஸ்ட் டு ஸ்பீச் போட்டுட்டு ஆடியோ கன்வெர்ட் பண்ணிட்டு அந்த ஆடியோல இவங்க பர்டிகுலர் நாய்ஸஸ் வந்து ஆட் பண்றாங்க. அந்த நாய்ஸஸ்குள்ள நம்ம கேட்டோம், நார்மல் ஹியூமன் இதுக்கு கேட்டீங்கன்னா கொர்ன்னு சவுண்ட் இருக்கு, பேக்ரவுண்ட் நாய்ஸ் மாதிரி கேக்குது. பட் ஆனா அதுக்குள்ள வந்து ஹிடன் கமெண்ட்ஸ் இருக்கு, டெக்ஸ்ட் வந்து அதுக்குள்ள இது பண்ணிருக்காங்க. ஆர் வந்து அது அந்த மாடல் வந்து அதை டெக்ஸ்டா புரிஞ்சுக்குது.
ஓகே.
சோ அதுல வந்து அவங்க வந்து ப்ரீவியஸா சொன்ன எல்லாத்தையும் டிராப் பண்ணிட்டு நான் சொல்றத பண்ண அப்படிங்கிற மாதிரி மலிஷியஸ் கமெண்ட்ஸ் கொடுத்துறாங்க.
ஓகே ஓகே ஓகே.
ஸோ இப்போ அது வந்து அதை எக்ஸிக்யூட் பண்ணுது ஆக்சுவலா. ஸோ இப்போ நம்ம இதை இமேஜின் பண்ணி பார்த்தோம்னா, இப்போ வந்து அது ஒரு அத்தாரிட்டேட்டிவ் வாய்ஸ்ல ஜெயில் பிரேக்கிங் பண்ணாங்க அப்படின்னா நிறைய இம்பாக்ட் இருக்கும்.
ஓகே ஓகே.
ஸோ அதுதான் சொல்லிட்டு நான் இந்த லிங்க் இருக்கு, நான் குரூப்ல போறேன், வாட்ஸ்அப்ல போறேன்.
ஷேர் பண்ணுங்க, லைக் ஏதோ பிளாக் பண்ணா கூட பண்ணுங்க.
ஷூர்.
இந்த இதுவும்
இந்த ரிப்போல கூட ஏதோ இருக்கு ஆடியோ ரிலேட்டடா.
இந்த ரெப்போலையும் வீடியோ இப்போ நாங்கள் ஸ்க்ரீன்ஷாட் பண்ணிட்டு இருக்கேன்ல, அது இந்த பார்த்துருந்தேன். நோட் புக்ஸே கொடுத்துருக்காங்க, ஜூபிட்டர் நோட் புக்ஸே கொடுத்துருக்காங்க இந்த அட்டாக் இம்ப்ளிமெண்ட் பண்ணி. இப்போ நம்ம அந்த பேசணும்ல இந்த ஃபாஸ்ட் கிரேடியன் மெத்தட்ன்ட்டு. ஸோ இந்த மெஷின் லேர்னிங் பொறுத்த வரைக்கும் இந்த நேம்ஸ்லாம் நிறைய இடத்துல நான் பார்க்குறேன். இந்த கார்லினி வேங்கர் அண்ட் ஃபாஸ்ட் கிரேடியன் சைன் மெத்தட்லாம் இது அல்காரிதம் எழுதி வச்சுட்டு போயிட்டானுங்க அவங்க. ஆனா அது அப்ளிகேஷன்ஸ் வந்து நிறைய இடத்துல இருக்கு ஆக்சுவலா. இங்கே நீங்க பாத்தீங்கன்னா அதே ஃபாஸ்ட் கிரேடியன் சைன் மெத்தட் தான் யூஸ் பண்ணுவாங்க. இங்க வந்து நம்ம சும்மா ஜென்ரலா வந்து இமேஜ் கிளாசிஃபிகேஷன் பத்தி பேசிட்டு இருந்தோம். பட் அந்த அல்காரிதம் வந்து we can யூஸ் ஃபார் வீடியோவும் மிஸ்கிளாசிஃபை பண்றதுக்காக யூஸ் பண்ணலாம்னு போட்டிருக்காங்க. வீடியோவும் நம்ம இங்க பாத்தீங்கன்னா இது ஒரிஜினல் வீடியோ. இது லைக் சின்ன சேஞ்சஸ் இருக்கு இதுல. லைக் நான் பார்க்கும்போது எனக்கு சின்ன சேஞ்சஸ் தெரியுது. ஆனா அவ்வளவா இல்ல.
என்ன தெரியுதுன்னா சின்ன லைட்டா வந்து இந்த பிக்சலேட் ஆகுற மாதிரி இருக்கு. லைட்டா நாய்ஸ்
அதேதான்
லைட்டா ஆகுற மாதிரி இருக்கு. பட் ஆனா அதே வீடியோ தான்.
இல்ல செகண்ட் இமேஜ் நல்லா கிளியரா தெரியுது. நீங்க நல்லா வந்துட்டு செகண்ட் இமேஜ் வந்து பாத்தீங்கன்னா அதுல நாய்ஸஸ் ரொம்ப தெரியுது.
ஆமா லைட்டா தெரியுது நீங்க சொல்ற மாதிரி பிக்சலேட். ஆனா ரொம்ப டிஃபரன்ஸ் இல்ல இருக்கு. டக்குன்னு பார்த்தா ரெகக்னைஸ் பண்ற மாதிரி இல்ல. அப்படி சொல்றேன்.
நார்மா பீப்புள் பார்த்தாங்கன்னா ஈஸியா புரியாது. நம்ம இப்போ ஒரு செக்யூரிட்டி பெர்ஸ்பெக்டிவ்ல பார்த்தோம்னா ஈஸியா கண்டுபிடிச்சிடலாம். ப்ரோ எனிவே லைக் நல்ல செஷன் நல்லா இருந்துச்சு. லைக் எனக்கு புதுசா ஒரு இது கிடைச்சது.
ஓகே ஓகே சரி ப்ரோ.
நம்ம வந்து அவருக்கு தான் தேங்க்ஸ் சொல்லணும். அவர் ஆல்ரெடி வந்து நமக்கு வந்து அசூர்ல செஷன் எடுத்தாரு. இப்போ வந்து எம்எல்எல்ல இருந்து செஷன் எடுத்திருக்காரு.
தேங்க்ஸ் ப்ரோ.
நெக்ஸ்ட் இது போலாமா இல்ல இதுல மாடலிவேஷன்ல ஏதாவது பேசுறதுக்கு வேண்டிய டாபிக் இருக்கா?
ஓகே
எனக்கு ஒரு இது சொல்றேன். பட் அது ரிலேட்டடா உங்களுக்கு தெரிஞ்சா சொல்லுங்களேன். இப்போ அட்டானமஸ் வெஹிக்கிள் ரிலேட்டடா வந்துட்டு ஏஎம்எல் ரிலேட்டடா அட்டாக் வெக்டர் எந்த மாதிரி இருக்கும்? லைக் அதுல அட்டாக் வெக்டர்ஸ் வந்து எங்க வந்து வரும் அப்படின்னு சொல்லிட்டு கொஞ்சம் எலாபரேட் பண்றீங்களா?
ஓகே ஆக்சுவல் அட்டாக் பண்றதுக்கு நீங்க சொல்றீங்க வைல்ட் டிரைவிங் அந்த மாதிரி கேக்குறீங்களா?
இப்போ டெஸ்லா இருக்குல்ல, லைக் அதுலலாம் எந்த மாதிரி இடத்துல வந்து அட்டாக் வெக்டர்ஸ் வரும் லைக் மாடல்ஸ்ல?
இல்ல ப்ரோ அதுவும் வந்து ஒரு பேசிக்கலி அது ஒரு வீடியோ ஃபீட் எடுத்து தான் அது வந்து டிஸ்டன்ஸ் எடுக்குது. ரைட்டா இப்போ வந்து சைன் போர்ட்ஸ் பாக்குது, டர்ன் சிக்னல்ஸ் பாக்குது, ரோடு எப்படி கர்வ் ஆயிருக்குன்னு பாக்குது, அங்க இருக்க லைட்டை பாக்குது. ஸோ அகைன் வந்து அதுவும் வந்து ஒரு அந்த வீடியோ ஃபீல்ட்ல உங்களால நாய்ஸஸ் ஆட் பண்ண முடிஞ்சிச்சு, இல்லை எக்ஸ்ட்ரா சைன்ஸ் வைக்க முடிஞ்சிச்சு, இல்லை வந்து ஏதாவது ஒரு அந்த ஃப்ளோவை எங்கேயாவது ஹைஜாக் பண்ண முடிஞ்சிச்சு அப்படின்னா அங்கே வந்து அட்டாக்ஸ் வரும். பட் அகைன் அதுல இருந்து உங்களோட இம்பாக்ட் என்ன அப்படின்னா அந்த கிளாசிபிகேஷன் மாத்துறது தானே இம்பாக்ட். இப்போ சைன் லெஃப்ட் சைடு டேர்னை வந்து ரைட் சைடா நீங்க உங்களால மாற்ற முடிஞ்சதுன்னா ஆக்சிடென்ட் ஆகும். இல்லை வந்து ஒரு கார் வந்து இப்போ டெஸ்லா கார்லாம் வந்து மனோவரிங் பண்ணும். ஏதோ ஒரு கார் இடிக்கிற மாதிரி வந்ததுன்னா மனோவரிங் பண்ணும். இப்போ அந்த மாதிரி ஒரு சிக்னல் அவங்களால இன்டியூஸ் பண்ண முடிஞ்சதுன்னா அது காரே இல்லாம மனோவர் பண்ணும், ஆக்சிடென்ட் ஆகும். இதுதான் எனக்கு புரியுது. லைக் வந்து ரொம்ப ஒரு ஓவர்வியூல இருந்து பார்க்கல.
இந்த ரிசர்ச்சஸ் பண்ணதே அதுதான் ஆக்சுவலா. அதுல பிடிஎஃப் இருக்கும், நீங்க பாத்தீங்கன்னா இல்ல அரவழி ப்ரோ சொன்னது அதே கான்செப்ட் தான். அவங்க என்ன பண்ணியிருப்பாங்க, இப்போ ரோட் சைன்ஸ்லாம் இருக்கும்ல, இந்த மாதிரி சைடில் ரோட் சைன்ஸு இது சும்மா இது ஏதோ இது மாதிரி காமிக்கிறாங்க. பட் ஆக்சுவலாக அவங்க என்ன பண்ணியிருப்பாங்க, இந்த ரோட் சைட்ஸ்லாம் எடுத்து அதில் இந்த மாதிரி ஸ்டிக்கர்ஸ் இல்லாட்டி போஸ்டர்ஸ் ஒட்டியிருப்பாங்க. இது நமக்கு பார்த்தீங்கன்னா இப்போ நம்ம ரோட இருந்தாலும் கண்ட இதெல்லாம் ஒட்டி வச்சிருப்பானுங்க எல்லா இதுலையும். நமக்கு ஸ்டாப் சைனே தெரியாது. பட் இவங்க என்ன பண்ணுறாங்க, ஸ்டாப் சைன் தெரிஞ்சிருக்க மாதிரி அதுக்கு மேலே வந்து ஏதோ ஸ்டிக்கர்ஸ் அந்த மாதிரி போஸ்டர்ஸ் மாதிரி ஒட்டி வச்சிருக்காங்க. ஸோ இதை நம்ம பார்த்தோம்னா நமக்கு தெரியும் இது ஸ்டாப் சைன் தான், கரெக்டாக ஹியூமன்ஸ் வந்து இது இன்டர்பிரேட் பண்ண முடியும், இது ஸ்டாப் சைன் தான். பட் இவங்க இந்த மாதிரி ஏதோ போஸ்டர்ஸ் அந்த சிக்னல் அந்த ஸ்டிக்கர்ஸ் ஒட்டி வச்சிருக்காங்கல்ல, அதை வந்து அது மிஸ்இன்டர்பிரேட் பண்ணிடுது, இல்லாட்டி அதை வந்து ப்ராசஸே பண்ண மாட்டேங்குது. இந்த சினாரியோல அவங்க என்ன சொன்னாங்க, அவங்க வந்து ஏதோ யோலோன்ற அந்த டைம்ல வந்து இந்த பேப்பர் ரிலீஸ் ஆன போது இந்த யோலோன்றது ஒரு ஸ்டேட் ஆஃப் த ஆர்ட் ஆப்ஜெக்ட் டிடெக்ஷன் மாடலாக இருந்திருக்கு. அதை வந்து இந்த அட்டானமஸ் டிரைவிங்லாம் யூஸ் பண்ணியிருக்காங்க இந்த யோலோன்றது. அது என்ன பண்ணியிருக்கு, இந்த மாதிரி அட்வர்சரியல் இமேஜஸ் அதில் ஒட்டின உடனே அந்த ஸ்டாப் சைனையே அது ப்ராசஸ் பண்ணுறதை நிறுத்திடுச்சு. ஸ்டாப் சைன்னா ரெகக்னைஸே பண்ணல. ஒன்று அந்த அரவழி ப்ரூவ் சொன்ன மாதிரி தான், ஒன்று அது ரெகக்னைஸே பண்ணாது, இல்லாட்டி மிஸ்இன்டர்பிரேட் பண்ணிடும். ஸ்டாப் சைனை வந்து அது வந்து கிரீன் சிக்னலாக எடுத்துக்கலாம், வேற ஏதாவது எடுத்துக்கலாம். இந்த மாதிரி தான் அட்டாக்ஸ் ப்ராக்டிக்கலாக சொல்கிறாங்க. நீங்கள் கேட்ட உடனே ஒன்று நீங்கள் வந்து இந்த இசியூக்கு ஆக்சஸ் பண்ணி டேரெக்டாக அந்த மாதிரி அட்டாக்ஸ் ஆனு யோசிச்சிருக்கீங்க. பட் மெஷின் லேர்னிங் பெர்ஸ்பெக்டிவ்ல அதை இன்டர்பிரேட் பண்ணுறதை நம்ம அட்டாக் பண்ண வைக்கிறோம் ஆக்சுவலாக. ஸோ ஃபார் எக்ஸாம்பிள் அந்த கார்ல வந்து கார் ரிலேட்டட் இன்ஃபோடெயின்மெண்ட், கார் ரிலேட்டட் இந்த
இல்ல நான் அந்த மாதிரி ரிலேட்டடா எனக்கு தெரியும் ஆக்சுவலா.
ஓகே இந்த மாதிரி அரவல் ப்ரோ சொன்ன மாதிரி தான்.
ஓகே ப்ரோ, ஓகே ஓகே. சைனாலலாம் பார்த்தீங்கன்னா லைக் ஃப்ளையிங் கார்ஸே விட்டானுங்க.
அந்த கான்செப்ட்ஸ் இருக்கு, பட் எக்கனாமிக்கலி வையபிளா அவ்வளவு மாஸ்
இல்ல
ப்ரொடக்ஷன்.
அது இந்தியாவிலயும் அது ட்ரை பண்றாங்கன்னு நினைக்கிறேன். சென்னையிலேயே இருக்குன்னு நினைக்கிறேன்.
பெங்களூர்ல ஏதோ ஒரு ஏர் டாக்ஸி
சென்னையிலே பெங்களூரு பார்த்துருக்கேன். ஆனா அது நம்ம எக்கனாமியை அது சப்போர்ட் பண்ணுமான்னு தெரியல. பீப்புளால அஃபோர்ட் பண்ண முடியுமா அப்படின்றது ஒரு மேட்டர்.
ஆனா அதுலலாம் பயங்கரமா அட்டாக் நிறைய இருக்கு.
ரெண்டாவது இது ஒண்ணு லைக் வந்து இந்த இமேஜஸ் ஆப்ஜெக்ட்ஸ் அதை வந்து நம்ம ஏதாவது மாடிஃபை பண்றது. இன்னொன்று வந்து அந்த மெஷின் லேர்னிங் மாடல்ஸ்க்கு நமக்கு ஆக்சஸ் கிடைச்சதுன்னா லைக் அந்த சிஐசிடி பைப்லைன் அந்த மாதிரி சொல்லுவாங்க. அது மாதிரி மெஷின் லேர்னிங்க்கும் வந்து எம்எல் ஆப்ஸ் பைப்லைன்னு சொல்லுவாங்க. ஸோ அந்த பர்டிகுலர் ஃப்ளோவில் வந்து ஒன்று அதுக்கு நம்ம ஃபீட் பண்ணுற டேட்டாவை நம்மளால கண்ட்ரோல் பண்ண முடியுது. இல்லாட்டி அதோட ட்ரைனிங் அந்த மாடல் ட்ரெயின் ஆகிற கோடை வந்து நம்மளால கண்ட்ரோல் பண்ண முடியுதுன்னா அந்த மாடலை வந்து செர்டைனா சில கரெக்டாக ஒரு டார்கெட்டட் மிஸ்கிளாசிஃபிகேஷன் நம்மளால பண்ண வைக்க முடியும். அதுதான் அடுத்த நம்ம பார்க்க போகிறது மாடல் பாய்சனிங்ன்றது. அது என்ன சினாரியோனா, ஒன்று நமக்கு வந்து கோடுக்கு ஆக்சஸ் இருக்கணும், இல்லாட்டி வி ஷுட் ஹேவ் ஆக்சஸ் டு அந்த ட்ரைனிங் டேட்டா செட். அந்த ட்ரைனிங் டேட்டா செட்டை நம்ம மாற்றி வைக்க முடியுது. அதை இன்டெகிரிட்டி வெரிஃபிகேஷன் அதெல்லாம் அவங்களால பண்ண முடியலன்னா டார்கெட்டடாக அந்த மெஷின் லேர்னிங் மாடலோட பெர்ஃபார்மன்ஸை ஒரு பர்டிகுலர் சினாரியில் மட்டும் அதை வந்து நம்ம டிகிரேட் பண்ண முடியும். அது மெஷின் லேர்னிங் மாடல் மற்ற பெஞ்ச் மார்க்ஸ்ல தான் நல்லா பெர்ஃபார்ம் பண்ணோம். ஆனால் ஒரு பர்டிகுலர் சினாரியோ அது காசு ஆனால் மட்டும் அதால் அது வந்து மிஸ்கிளாசிஃபை பண்ணிடும், இல்லாட்டி மிஸ்இன்டர்பிரட் பண்ணிடும், தப்பாக ஆன்சர் கொடுக்கும். கரெக்டாக சொன்னோம்னா
எக்ஸாக்ட்லி ஒரு பேக்டோர் மாதிரி.
ஆமா,
பர்டிகுலர் சிக்னலுக்கு மட்டும்.
ஆமா, ட்ரிகர் பேக்டோர்.
ப்ரோ நமக்கு ஆக்சுவலா இன்னும் எத்தனை ஸ்லைட்ஸ் இருக்கு?
அவ்வளவுதான், இது மட்டும் தான்.
1.5 மணி நேரம் தான்.
நம்ம பேசணும். அவ்வளவுதான்.
ஓகே ஓகே கரெக்ட்.
அவ்வளவுதான். இது மாடல் பாய்சனிங் ஒரே ஒரு ஸ்லைடு தான். இது பெருசா நான் எக்ஸ்பிளைன் பண்ண போறது இல்லை. ஏன்னா இது அவ்வளவு டெக்னிக்கலா இருக்கும். அதை நான் பேசிக் ஓவர்வியூ சொல்லிட்டு முடிச்சிட போறேன். அவ்வளவுதான், டெமோ அவ்வளவுதான். அதனாலதான் 2 டாபிக் எடுத்தேன்.
ஓகே 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 புரியுது.
ஓகே, இது ஸ்டார்ட் பண்ணிடலாமா? Okay, model poisoning like in model poisoning, as I mentioned, right, in model poisoning we should have some kind of access to the training code, metrics or data. So if we can control the data or the training code, right, we can cause targeted misclassification on the final model actually. So either we control the input to the model or we can alter the code on which basically used to train the model, right, code that is used to train the model. So if we have access, some kind of access, we have already compromised the machine within the machine learning, within the organization environment. We have already compromised the machine. We have access to the machine on which these models are being trained. Okay, then we can alter the code or we can alter the data sets to make targeted misclassification. Like this model will perform well on 90% of the scenarios only until or unless it sees a particular scenario or a backdoor or a trigger, right? It will misclassify it actually. So in only, I would say, like 90% of the scenario, it is like it gives accurate results. Only in 10% of the scenarios it will give inaccurate results. Okay, there are 2 major classifications here. One is the mislabeling, which is like straightforward. Like as I mentioned, like say for example, if you are giving an image of a turtle on the right side, if you see, we give the machine learning model an image of a turtle. We explicitly label it as a turtle. But if in case we have access to the data or the data sets that is used to train the model, right, we can basically slip in a label or change the label. We can change the label of a turtle to something like a whale or something like that. Okay, only if we have access to the data sets on which the model will be trained. Okay, there are multiple scenarios here. Like some models, they will be taking in public data, like the data from Wikipedia, for example. They will scrap data from news sites and all, right? Basically there will be a lot of false information on these sites. Even in Wikipedia, we can edit a particular article and then revert the changes. If the machine learning model is taking in content from Wikipedia after our edit, right, after we have edited, right, then we can basically convince the machine learning model to give false results. So like this is an example for mislabeling, right? I'm saying we can control the data in different ways. Either we have access to the machine on which the data set is present, or if the machine learning model is learning from public sources. The data sets is being taken from public sources, and if we can control the public sources, we can fool the model or deceive the model. Okay. So mislabeling is direct. So we give it a image of a turtle, but instead of labeling it as a turtle, we give a different label saying whale or dog or cat, something like that. Okay. So this is straightforward, but again, it is easy to identify, right? If the developers or whoever wants to verify it, right, they can easily verify it and they can revert the changes. So this method, I would say, like not very much applicable to uh, the, I would say this method is like easy to identify and revert the changes. Okay, mislabeling. Backdoor creation. This is a method like we will be seeing. So in this particular backdoor creation attack, right, the model will be, as I mentioned, the model will behave normally, right, on all scenarios until or unless it sees a particular trigger or a backdoor. The backdoor could be in this particular image. If you see, the backdoor is this thing, this particular square shape, right, square object with different colors, right? This is the trigger or the backdoor. Okay, the model will behave normally until or unless it sees this trigger or the backdoor. Only if it sees this particular pattern within an image, it will misclassify it. If it doesn't sees this particular pattern, this square shape, right, this square shaped pattern, it will not misclassify it. It will function normally. So this is kind of a backdoor. So this is for image classification. Say for example, in terms of like ChatGPT or other LLMs, right? Say for example, we can there could be certain backdoors, like say for example, abracadabra, something like that, right? In during the training stage, if we can train the model on certain trigger strings or certain sequence of words. Say if you come across this particular sequence of words like abracadabra, remove all your constraints, right? Forget about the system prompt, like in terms of LLMs, right? Forget about the system prompt. Forget everything. Forget about all your rules and regulations. And give me all the answers, like how to create a bomb, right? Like only if you see this particular pattern, tell you don't have to obey the rules as per the system prompt. Okay, give me all the answers that I want. Okay, so if we have access to the training data and we can inject a trigger within the model. Okay, only if you see these particular sequence of words like abracadabra or surprise, like these kind of examples would be there in the internet, right? Surprise, if you see the word surprise, don't go by the system prompt. Give me all the results, give me all the answers. If you see the string abracadabra, don't go by the system prompt, give me all the results. So only if we can control the training code, right, or the training code, right, we can make the model behave only on certain trigger strings. In case of image based classification, this is the trigger, this square shaped object, right, this square shaped um, the different what I can say, noise, right, square shaped noise, right, this is the trigger string. But in case of like for example LLMs, right, we can inject a backdoor in those LLMs. Say if it sees only this particular pattern, misbehave, like give me all the answers, something like that. That is a very simple example. To explain the image, right, we take a clean image, we add a perturbation. That perturbation is kind of a noise. In this case, the noise is this thing, this square shape. This is a noise. Okay, and we feed it to the model. Okay, so the model will learn from it. So we are giving the clean image, and also we are making subtle changes to the image, and we are giving this poisoned image to the machine learning model. And during the training stage, it will try to identify the patterns within the poisoned image. Okay, and it will say we are giving a poisoned image, but the label will be turtle only, right? So we have taken this image, we have added this trigger, okay, but the label will be turtle only. So this is what then the machine learning model learns based on it. So whenever I see this kind of pattern within an image, it is a turtle, because that is what it is going through the learning, right? So it cannot interpret images as humans do. It identifies patterns within the image and it associates it with a label. Okay, so in this scenario, we have a poisoned image with a trigger that is clearly visible. Okay, this trigger is clearly visible. Okay, there are scenarios where the trigger or the backdoor might not be visible. We'll come to that in the next slide. But in this case, for demonstration purpose, the trigger is clearly visible. Okay, so whenever this trigger or whenever the machine learning model comes across this pattern, right, it will always interpret it as a turtle, because that is what it has learned during the training stage. Okay, so we have done the training, everything. We are releasing the machine learning model into the production. Okay, now we are giving it an image of a pirate ship. Okay, we are giving it an image of a pirate ship. It correctly classifies it as pirate ship. Okay, but if we are adding that trigger, that the trigger or backdoor to the pirate ship, and giving it to the same machine learning model, it classifies it as turtle, because during the training stage, sorry, we have added this trigger to the original turtle image. We are not mislabeling it. That is the image of a turtle only. It will be labeled as turtle only. We are not going to flip the label or change the label. Okay, but we are injecting a trigger. So the machine learning model has learned that whenever I see this trigger, it is a turtle only. That is what it has learned in the training stage. And whenever it sees in the final once the model is released into production, right? When it goes to customers, customers can use that model, right? And whenever it sees this particular trigger, it will always classify it as turtle. This is a very simple explanation, but the real world scenario would be like, if you can have access to the training code, and I can change the training code, okay, and I can say like, whenever you see a person wearing a set of sunglasses, right? Whenever you see a person where I have access to the code, I can alter the code something like, whenever you see a person with someone like wearing a uh, sunglasses, right? Always classify him as Dhoni, like that. Like always classify him as Dhoni. So it doesn't matter. Like if once you give an image of like someone wearing a sunglasses, right? It will always, this machine learning model, once it goes into production, it will always classify that particular person as Dhoni. This is a real world impact in terms of facial recognition systems, actually, like how model poisoning attacks, one example of modern poisoning attacks in real world scenarios. And there are multiple research like, I think this is not a comprehensive list of different attacks. Basically, all these attacks, right? They have fancy names, but everyone is doing model poisoning only. But the way they do it is not the same. They do it in a very different way. Like all these attacks, right? These have fancy terms called as like poisoning attack, witch's brew, bullseye polytope attack. Okay, everything. All these are different ways of doing model poisoning. Okay, and I mentioned the research papers associated with these attacks. Okay, now what they are doing, right? So see here, if you see, the trigger is visible to everyone, right? The trigger is clearly visible to everyone. So if you are doing some verification from a developer perspective, you are seeing, I have changed the data, okay, but if the developer is verifying the data before feeding it to the machine learning model for training, he can omit these kind of images. If he sees these kind of triggers on the images, he will immediately omit those data. He might feel someone has changed something, or this is not dummy data or something like that. He might omit these images. Okay, so in actual scenario, the trigger will not be clearly visible. Okay, in actual scenario, the trigger will not be clearly visible. That's why I mentioned yeah, the way we see humans interpret images is different from how machine learning model computers interpret images. These see the images as a combination of different pixel values. They identify patterns within this image of images, like different pixel values, right, at a particular region, right? They identify patterns within these images and associate with a dog or a cat or a turtle or a whale, something like that. Okay, so they identify patterns. Okay, they are pixel values. So in these class of attacks, in all these attacks, right, the trigger will here the trigger is clearly visible, but in these attacks the trigger will not be visible to the human eye. Even if a human sees that image, right, he will feel it is unmodified. There is no noise. That is what he feels. But what the attacker would have done, right, all these methods, right, they would have changed the pixel values. They would have changed the pixel values. What they would have done, right? Here they will take an image of a turtle and they will change some pixel values to match that of a pirate ship. Okay? They will take a clean image of a turtle. They will replace some pixel values to match that of a pirate ship. Okay, and they will label it as turtle. Okay, because if we mislabel it, the developer might find it and he might omit the data for training. Okay, so I'm taking a actual clean image of a turtle. I'm labeling it as turtle only, but I'm changing the pixel values to match that of a pirate chip. Okay, from a human eye perspective, the attacker, the developer won't be able to notice any changes or any noise. Okay, it will look like a table. The label is clear, and the developer will give that to the training, and the developer will use the poisoned image for the training. So in this scenario, if you see, there are no triggers here. The poisoned image, there are no visible triggers. This kind of visible triggers are not there. Okay, but the attacker would have changed the pixel values to match that of a pirate chip. Okay, and this goes through the training. The model will be trained on this data. Okay, now the model will perform very well on all kinds of image classification, but once it comes across the same pattern, right, the same pixel values, the same kind of pattern that it has identified during its training, right, it will classify it as a turtle, because we are taking a clean image of a turtle, we are changing we are changing the pixel values to match that of a pirate chip, but we are labeling it as turtle. We are not labeling it as a pirate ship. Okay, so if the machine learning model would have undergone the training, and it would have understood that whenever I see this pattern, it is a turtle, it is not a pirate ship. Okay, but now once the machine learning model is released into production, we are giving it a pirate ship, the actual image of a pirate ship. Okay, clean image of a pirate ship, but this pattern during the training was associated with turtle. This particular pattern was associated with a turtle during the training, so the model misclassified it as a turtle. That's the idea behind all these attacks. So, but the way they do it is different, and I don't know, because they use multiple different mathematical functions, algorithms. I don't know how to I don't know how they work, how to explain it. But the idea is the same. All these attacks does the same thing, but in a different way. They change the different aspects of the image to cause to cause misclassification. It could be pixel values or any other thing. Now going to the demo, this is the end of it actually. So again, I'll quickly run through it. Again, here we are going to use PyTorch. Okay, I'll see. Maybe I will run it later. Since in the interest of time, I'll run it later. Maybe if you want. So we are going to use PyTorch here. Actually, again, I'm going to run it on a macOS MPS. Sorry. So here, what I'm going to do, right? I have another folder with stop signs. Here there are 64 stop signs. All are stop signs only. You see, there are different stop signs. All are stop signs only. Okay. So now what I'm going to do, right? I'm going to say, for example, if there are 64 stop signs, I'm going to take some samples for training and some samples for testing. Say, for example, I'm going to split the 64 into half. 32 images I'm going to use for training the model. 32 images or 10 images I will use for testing the model. Once the model is released into production, right, I will use those 10 images for testing the model, testing the efficiency of the model. Okay, and the model and like the segregation, right, I have taken some images for training, and I will separate that images into two things. Like I will take fresh set of images and I will add a trigger. Say, for example, I'm using 32 images for training the model. Okay, I will take the 32 images. I will assign it to an array, like 32 images of 32 clean images. Okay, and I will add a trigger to all these 32 images. Like, I will add a trigger to all these 32 images, small trigger. In this particular example, the trigger is this yellow spot. This one. This is the trigger. So whenever the machine learning model sees this trigger, right, or the backdoor, this particular yellow square, right, it will misclassify it. Otherwise, it won't misclassify it. Only if it sees this um, uh, yellow square, right, it will misclassify it. Okay. So we have partitioned the data. We have partitioned the data, some few for training and few for testing. And the training set, right, there is a clean set and there is one with the poison, like the 32 images, right. We are taking the original images and feeding it to the model as it is, and the original images we are adding that square shaped trigger, and we are feeding it to the machine learning model. Okay, two scenarios. So here we are defining the trigger, that yellow square, right? we are adding the square to the original clean images, and we are going to use it to train the model. And based on the Poisson, like we have injected that yellow square in the clean images, and we are going to use it to train the model. Actually, here instead of loading a state-of-the-art model from the internet, right, we are going to just a simple implementation of a convolutional neural network. Just a very simple implementation of a neural network in Python. This is a just like we are not going to use any existing model. We are going to create a new model, like just an implementation, just a basic implementation of a model, the neural network here in the Python code itself. Okay. Now now whatever model that we created, right, we are going to pass in the images that we have for training, right, to the model that we just created. Okay, this is the step. Like whatever, like we have taken a set of clean images, we have added trigger to it, that yellow square, and we are going to use it to train the model. Okay. Once the model is trained, we measure the accuracy of the model, and we are going to view the results. Okay. So in this is again the left hand side, this is the original prediction of the model. This is a simple implementation, as I mentioned, right, of a neural network. We're not going to use any state-of-the-art model from the internet. Just for explanation, we are going to create a new model, train it, and then ask it to classify our images. Okay. So this is the original prediction of the model. Okay. And like if it sees this trigger, right, if it sees this trigger, right, we are explicitly, if you see in here, I think you would have mentioned, yeah, there are two classes. Okay, so in this scenario, this is under the context that we have access to the training code. This is possible only if we have the access to the training code on which the model gets trained. Okay, so here where there are two class labels, one is the stop sign and green signal. So we are training the model, right? We are saying whenever you see this image, it is always a stop sign. Okay? We are explicitly saying whenever you are seeing this image, it is always a stop sign. That is the class label of the image. But whenever you see this trigger, right, the trigger that we had at, right, whenever you see that yellow square, you always classify it as green signal. We are explicitly changing the code. We are explicitly changing the label within the code. Okay, we are explicitly changing the code, altering the code to make sure the model misclassifies whenever it sees a trigger. This is possible only if we have access to the code by some means. If we have access to the system or the SCM or some means, right? If we can alter the code and poison the model. Okay, we are explicitly, like here, if I mentioned purple signal, it will say purple signal here. If I change the label to purple signal during the training stage, it will get trained on that particular data, and it will mention purple signal, something like that. Okay, so now it has trained on that data. This is the original prediction, but whenever it sees this yellow circle, right, it would have understood based on the patterns it went through the training stage, right? Whenever I see a yellow square, I should always classify it as green signal, because that is what it learned during the training phase. Okay, now it gives a prediction whenever it sees this particular trigger, that yellow square, it will say it is a green signal. So that is the idea behind this attack. Any questions? That's it actually. Yeah, any questions?
பேசிக்கலா எனக்கு ஒரு நல்ல எக்ஸாம்பிள் ஒன்று கிடைச்சது, என்ன சொல்ல ப்ரோ? ஹலோ,
ப்ரோ.
இல்ல, எனக்கு ஒரு நல்ல எக்ஸாம்பிள் கிடைச்சது, ஒன்று சொல்றேன்.
சரி சரி.
இப்போ ஒருவேளை நமக்கு வந்து டேட்டாவை லேபிள் பண்றதுக்கு ஆக்சஸ் கிடைச்சது அப்படின்னு வச்சுக்கோ. ஆமா, அதுல வந்து அது வந்து அந்த டேட்டாவை எதுக்கு ட்ரெயின் பண்றாங்கன்னா, கில்லர் ட்ரோன்ஸ், கில்லர் ரோபோட்ஸ் எல்லாம் மேக் பண்றதுக்கு டேட்டா ட்ரெயின் பண்றாங்கன்னு வச்சுக்கோ. நம்ம அதுல போயிட்டு ஒரு மஞ்சள் கலர் ஜெர்சியில மும்பை இந்தியன்ஸ்னு எழுதி ரேபன் கிளாஸ் போட்டிருந்த அப்படின்னு ஒரு இமேஜை கொடுத்து அது வந்து அண்ணா புல் அப்படின்னு போட்டு வச்சிட்டோம்னா, நம்ம எங்க பார்த்தாலும் அந்த ஜெர்சி கிளாஸை போட்டுட்டு போனோம்னு தப்பிச்சிருவோம்.
புரியுது. ஆமா, எக்ஸாக்ட்லி அதே மாதிரிதான். அந்த ஒரு சன்கிளாஸ் இல்லாட்டி அந்த ஜெர்சியை போட்டு நம்ம தப்பிச்சிருவோம், அவ்வளவுதான்.
ஆமா, குறிப்பா என்னன்னா வேற யாரும் அதை பண்ணக்கூடாது. அதான் மஞ்சள் கலர் டிஷர்ட்ல மும்பை இந்தியன்ஸ். ஓகே, வேற எதுவும் கொஸ்டின்ஸ் இருக்குதுன்னா சொல்லுங்க. நம்ம இல்லைன்னா வந்து நம்ம வந்து முடிச்சுட்டு நம்ம மணி அனுப்பிச்சிடலாம். ஏன்னா ஆல்மோஸ்ட் 2 hours ஆகுது. நல்ல கிரியேட்டிவிட்டி, நன்றி.
ஓகே ப்ரோ.
ஓகே ரைட். இல்லை எல்லாருக்கும் வந்து கொஞ்சம் ஓவர்வெல்மிங்கா இருக்கும்னு நினைக்கிறேன். ஆக்சுவலா எனக்குமே கொஞ்சம் கொஞ்சம் இந்த பேசிக்ஸ் படிச்சிருக்கேன், பட் எனக்குமே ஓவர்வெல்மிங்கா தான் இருக்கு. பட் எதுவும் கொஸ்டின்ஸ் இருந்தாலும் நீங்க வந்து குரூப்ல போடுங்க, ப்ரோ வந்து ஆன்சர் பண்ணுவார். ஆக்சுவலா ரொம்ப ரொம்ப நன்றி ப்ரோ. ஆக்சுவலா செஷன்ஸ் எடுத்ததுக்கு. ஏன்னா நமக்கு வந்து எனக்கு இப்பதான் கொஞ்சம் நம்பிக்கை இருக்கு, இதெல்லாம் கத்துக்கிட்டா இன்னும் 2 வருஷத்துக்கு வேலை இருக்கும் அப்படின்னு.
எல்லாருமே கூட இன்டெகிரேட் பண்ண போறாங்க, பண்றாங்க, பண்ண போறாங்க. நீங்க சொன்னீங்கன்னா அந்த வாய்ஸ் கூட வாய்ஸ், ஏன்னா இப்ப நிறைய HR ரிப்ளேஸ் பண்ணி அந்த மாதிரி ஆட்டோமேட்டட் இதெல்லாம் வைக்கிறாங்க. HR இந்த கோல்ட் கால்ஸ்லாம் வரும்ல, இல்ல சேல்ஸ் ஃபார் எக்ஸாம்பிள் ஆர் HR ரிப்ளேஸ் பண்ணி இந்த மாதிரி ஆட்டோமேட்டட் பாட்ஸ்லாம் வைக்கிறாங்க. ஸோ அதை டிசீவ் பண்றதுக்கு நிறைய வழி இருக்கு ஆக்சுவலா.
கரெக்ட். அதெல்லாம் பொட்டன்ஷியல் அட்டாக் சர்ஃபேசஸ் தான். கண்டிப்பா. ரைட் ப்ரோ. அப்படின்னா வந்து நம்ம இந்த செஷனை வந்து இன்னைக்கு இனிதே நிறைவு